site or any.
You all see my screen?
Yes.
Excellent. Okay, well, thanks for the introduction. So I'm Jeff. I'm the technical lead for Open Force Field. We've been going for 3 years now, and we've had the experience of taking finite resources to accomplish a defined set of goals, and one of those goals is doing reproducible open source science. I'm hoping that in this talk, I can share our kind of in the trenches experience on what's worked at the interface of kind of fast moving research code and stable deployable open source software. A little bit of background on us first. So we are Open Force Field. Our particular scientific domain is doing atomistic simulations. For example, on the right here, I'm showing a small molecule binding to a protein. This is a small molecule inhibitor binding to bromodomain 4. The physical model underlying this simulation is a force field, and that describes how the atoms pull and push on each other in this physics-based simulation. And you're probably looking at this thinking, oh, cool, hey, look at that. Let's go solve all sorts of stuff. But one of the many issues with these simulations is that they are pretty darn hard to set up from the common sorts of input data. And about half the ways where you thought that you would set it up right, you've actually set it up wrong and shouldn't really expect correct results. So there are a few software ecosystems that let you set up and run these sorts of simulations, but it's a really large training investment to get running with any of them, especially correctly. And this wasn't a great experience for users. So especially pharmaceutical industry users who would watch all these amazing papers come out using these simulation-based methods, but they couldn't in practice apply the methods to their own problems because they couldn't relearn a whole ecosystem on a rapid basis and then wire it into their industry workflows. So the Open Force Field professors had this project in mind, and our first supporters actually came from industry. The pharma industry wanted to get in on sort of the action from these simulations, and they were happy to support this open source model because it meant that they won't get stuck later with licensing fees, and that it committed the work all to a pre-competitive space. So other companies would be free to pitch in without sort of any strategic problems. So the goals of Open Force Field are to make force fields easier to use, create, compare, and extend. And as sort of a byproduct of this, or proof of concept, to actually make a new force field separate from the existing ecosystems in the process. And I think that this is a really great set of incentives for us, especially the use incentive, because my experience with scientific software has been that it's hard to actually bring into practice. But we have this great incentive where if people in pharma industries can't actually install and use our software, then we stop getting paid. So that's been really great in aligning our work. So we formally started in October of 2018 with 2 full-time staff, and I'm the more engineering focused of them. We didn't do nearly everything, us first 2 employees. Initially, a lot of our software and research deliverables relied heavily on fairly hands-on engineering work from grad students, postdocs, and PIs. One neat thing is that part of our initial contract for employment was that we had to sign saying that everything that we made would be MIT and BSD3 licensed, which are permissive open source software and data licenses. And I thought that was really great. And we had a lot of support from the top, from the professors on this project, to make everything infrastructure first. And so the model was that we'd have a small core team maintaining shared software. Researchers would use this shared software to go off and evaluate any new ideas they had for protein and small molecule modeling. And then anyone at any point can go and see this work being done that's come out in a publication or in a new data set, and they can use these new developments, they can bring them to bear on their own questions. So pretty soon after our launch, I made the first toolkit release that didn't require any licensed software dependencies, so it's all open source. This was based on a lot of work from before I got there. And about a year after our launch, we had the infrastructure going to make a new force field, which is a data artifact that underlies these physics models. So early on, there was a lot more research going on in the different open force field labs, that is with the grad students and postdocs, than us 2 full-timers could really monitor. And so we had to be fairly deliberate and intentional in how we engaged with these researchers' codes. One of my major goals was to ensure that grad students and postdocs could walk away when they're done, so they graduate or they go to their next academic role, and that they're not getting burdened with maintenance work that they're not paid to do, which is sort of the common way if you've done academic software development. And one of my lessons learned from this experience is that you want to have a kind of funnel for staged engagement based on the stage of the project. And this is sort of a compromise where I think that we're being genuinely helpful to the researcher and we're giving them some peace of mind about their results. So there's probably not any methodological errors and a solid guarantee of a handoff when they leave for their next role. And so the stages that we generally go for is at the project start, we push them to start with this project template. So this is a code repository template called the MolSI cookie cutter. MolSI is a center for computational molecular sciences. And so we push them to have basically open source dependencies that are easy to install and to follow this basic template that has continuous integration tests that's ready for other testing frameworks. It bundles in templates for documentation and versioning, and it interoperates well with Python deployment channels. And then for a long time, once they have that basic structure in place, we just stay out of the way and they do whatever experimentation they want. As a project progresses, the infrastructure team will sort of gently push for testing, but we don't make them test every line. And one of the ways that we keep things sort of manageable is when they need new functionality, we heavily prioritize putting that into our core software. And that way they're not going out and finding a different piece of software and eventually they have 15 dependencies to do parts of a pipeline. We encourage them to go through our core software, especially if we see that they're iterating on a certain design or method where we know that they're going to need new options faster than we make software releases. We'll put in a plugin for part of our core logic, or a plugin interface for part of our core logic where they can substitute in sort of their steps in the major pipelines. Around the time that a researcher presents at group meeting or has a cool data set that they want feedback on, we start pressing the question of which exact code did you use to generate this data? And this naturally segues into the concept of versioning, and this brings in occasional code reviews. And this is where we start making the decision about if the researcher is interested in sort of becoming a long-term maintainer for the code, or if they want to get it to the point where it's appropriate for publication and then be done with it. One great way to integrate code and reproducible science is with a service called Zenodo. So Zenodo will assign code bases DOIs for each versioned release that they make. And we found it to be really helpful. And then sort of the end of the researcher's involvement comes after their final publication. And that's when we decide whether we want to keep their code in its own place or start integrating it into our core tools. So a really important kind of reproducibility when we're looking at these projects is the data reproducibility. And this is super important for when other people want to replicate a complex process or for training new team members after an old one leaves. And of course, generally, reproducibility is great for advancing science. And so one method that we've arrived at by trial and error is to keep all analysis code in a GitHub repository. And this isn't necessarily a repository that turns into a deployable package by itself, but this is a repository where we keep track of the state of the analysis code, and then we make GitHub releases at certain points in that GitHub repository, and that records the exact state of the analysis code when the data was generated. Attached to this, we have this metadata. So here's an example of a release of kind of a glue code repository that we have on GitHub. It has sort of a scientific write-up for what happened in it. And then also in this assets section, we have a number of the exact inputs and outputs that happened during the process. And then here's an example showing the folder structure for all of the data that went into doing a certain process and making an output. On the infrastructure side for doing good reproducible science, it's really important to have meaningful versioning, to be a good neighbor to other open source projects, to strictly indicate behavior changes in release notes, to make sure, like I said, if people can't use our software, then they shouldn't be paying us. And so we have tests that run every night that follow our recommended installation pathway to make sure that nothing's changed in the world that would prevent our software from working. And also, especially when your package depends on other packages, to not clog any sort of environment resolution that needs to happen. And just like before, for the data repositories, we do GitHub releases of course, our infrastructure packages. Following our GitHub releases, we do conda packaging of our infrastructure. And also one thing that we found to be really helpful is making these sort of single file tarball installers where you get a really large zip file. And this doesn't have to go on, when you install this way, you don't have to go on the cloud, you don't have to go resolve your dependencies in real time. You get a specific configuration of all the dependencies packaged in a way that will just pop up and run on your computer. So computational molecular sciences has had a really hard time with data formats. There's a lot of really well-intentioned file converters that look harmless on the surface, but when you chain a bunch of them together and they're each making these sort of seemingly harmless assumptions about their inputs and being a little bit lax about specifications, because that's how things are in practice, when you put a lot of them together, you end up getting a really bad end result. And so we've learned to be really deliberate about which formats we load, and we may have disappointed or hopefully educated some users with these error messages. We're also doing force field science in a way that no one else really has before. And so for this reason, we had to invent a new specification. There was no appropriate previous specification for this. And so we're maintaining the Smirnov force field format specification so that other developers can interface with us. And so speaking of developer input, one of the trickiest things to balance is direct engagement with other open source software projects. So for really adjacent projects, this engagement can be pretty passive. So you see another package that you work with, you use the same sorts of formats, and you can engage with them passively. You can just sort of give them advice and chat with them maybe once a month to make sure that everything's in line. The tricky thing is when code changes are needed to make a new interface between conceptually different packages. So this would be where your object models don't really line up. And at that point, it becomes fairly costly and somewhat political to interface with other projects. So we got a grant supplement from the NIH to do exactly this. We're working to become interoperable with the MOSDEF framework. And this community focuses a lot more on material simulation. So recall that we're a biomolecule simulation group. And so a lot of the object models are fundamentally different. And so we got the supplement from the NIH to do this. And this grant is really gracefully diffusing a lot of this tension, because instead of looking at as, how little personnel time can we invest in this to kind of check the box, instead we have these resources and we're saying, well, okay, we have about a year of engineer time. What is the coolest thing we can reliably pull off in this time?
Jeff,
and what's great,
this is very, very cool work. And we have, we're coming up on the very, very end.